Can you all hear me? Hello?
Yes, sir.
Okay, so we will wait for a few minutes more. Let some other people join, then we will start at 7:10. And I have shared a slide. My screen is visible to all of you. Yes, is my screen visible?
No, sir.
You can you can see my screen.
Oh,
I
yes,
have
sir.
shared I have shared a slide. Atomic molecular physics interaction session 4.
Yes, sir. Yes.
Okay. So I hope my voice is clear to all of you and my screen is also visible to everyone. So let's now start today's session. Hello everyone, I welcome you all again for this interaction session on atomic and molecular physics, which is being flowed this January 2024 session in NPTEL with course code NOC24 Physics 04. Myself, Vivekananda Nayak. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So let's continue our discussion from the last class. So in today's session, we will basically solve a few problems which will be based on the week 4 lectures. That includes mainly the introduction of electron spin Stern-Gerlach experiments, then the vector atom model, like how the orbital magnetic moment and orbital motion and spin motion of the electron result in angular momentum, and then from that angular momentum there arises the magnetic moment, and due to the interaction between these two magnetic moments, then there is another new type of angular momentum which is called a total angular momentum. So we will solve a few problems related to all these things. So let's start with the first problem. The first problem says an electron moving around the nucleus is placed in external magnetic field B if L is the orbital angular momentum vector, L is the orbital quantum number, if capital L is the orbital angular momentum vector, small l is the orbital quantum number, and ml is a magnetic quantum number, then theta will be the angle, and theta is the angle between magnetic field vector and L vector, then what will be the value of cos theta? The options are option A, ml by L, option B is ml by L plus 1, option C is ml divided by L into L plus 1 root over, then option D is ml into L plus 1. So can anyone tell me what will be the correct option? You can hear me properly now? I need some confirmation whether my voice is clear to all of you or not.
Yes, sir. Yes, sir.
Okay, so I will give you a few minutes to please try this question, then we will discuss after a few minutes. Yes, so can anyone tell me what will be the correct option? What will be the value of cos theta? Anyone?
Uh, it's option C.
Yes, exactly. The option C will be the correct option,
C.
because now if you see in the last class we talked about the magnetic moment of the orbital magnetic moment due to the orbital motion of the electron, and we know electron. So we know according to Bohr's theory, electron is revolving around the nucleus in certain energy levels or energy states. Now, after the modification of the Bohr's theory by Bohr Sommerfeld theory, then there was quantization of other things like there was quantization of space also, due to which there was another quantum number introduced, and from that we know that the each energy level consists of a number of orbitals. So in last class we calculated So if there is a if the electron, we know electron is a charged particle. So when electron is revolving around a nucleus in certain orbit, then that electron will act as a magnetic dipole, and since it is acts as a magnetic dipole, it will be having its dipole moment. So if you remember, if you recall the last class, we solved that. So we solved mu. Wait. So in the last class we did mu is equals to I into A, where A is the area cross section of the orbit, which is pi r square, and I is the current, which is q by t. So from that, when we use the Bohr's model, that is mvr is equals to nh by 2 pi. This is from Bohr's postulate. So if by combining these two, we get, because this is nothing but L, so we get mu will be, the L vector will be E by 2m into L vector when we're talking about the magnitude. But since electron has negative charge, so in vector notation, we can say mu L vector is equal to E by 2n into L vector, and there is a negative sign. So if you see, since the electron has negative charge, if the orbital motion of the electron is in one direction, or the orbital angular moment, then this is orbital angular momentum. This is orbital angular momentum, and this is orbital magnetic moment. So if you see, both are oppositely directed. So suppose an electron is moving such that this is a suppose the electron is moving in this orbit. Suppose this is the electron is moving. So if this is the direction of L vector, then mu L will be in the opposite direction, because the charge of the electron is negative. So then again, from the quantization principle, we know that L vector is nothing but L into L vector mod is L into L plus 1 root over into H cross. And when the electron is placed inside a magnetic field, then what will happen? Suppose, so now let's consider, now here there is no B field. So B vector is 0, but when there is a magnetic field, suppose this is the direction of magnetic field. So can you all see what I'm writing? Can you all see it clearly?
Yes, sir. Yes, we can.
Okay, so suppose there is a magnetic field which is acting along z direction. Suppose this magnetic field is acting along z direction, and the electron is revolving in an orbit. So that, suppose this is the motion of electron. So if this is the center of the orbit. Suppose let this is L vector, and the angle between magnetic field and the angular momentum vector is theta. So since it is an electron, so its magnetic moment will be acting in the opposite direction, that of L. So we know, if a magnetic dipole is placed inside a magnetic field, then it will experience some torque. So now this torque will result in the revolve. Due to this torque, this angular momentum will be revolving around the magnetic field. Now the torque acting on that is mu L vector plus B vector. So due to this torque, there will be a motion around this magnetic field where the angle theta will remain constant. Now this angle of revolution, this revolution is called as Larmor precision, and the frequency of revolution we called it as Larmor frequency. This is Larmor precision. This is Larmor precision. And if you talk about the Larmor frequency, then what will be the value of Larmor frequency? Then Larmor frequency will be EB by 4 pi m. This is the value of Larmor frequency, which is omega L. So with this frequency, the the electron orbit will precede around the resultant magnetic field. So since there is a, suppose this is magnetic field B vector and this is L vector, then this is angle theta. Now we know L vector is L into L plus 1, this is small l, root over into h cross. So since there is an angle between magnetic field and angular momentum is Lz, then according to the quantization principle, Lz is again ml h cross. So we get L vector mod equals to L into L plus 1 root over h cross and Lz vector mod is ml h cross. Then what will be the value of cos theta? Cos theta will be nothing but Lz by L because this is theta, so Lz will be the component. So cos theta will be Lz by L. So putting these values, it will be ml h cross divided by L into L plus 1 root over into h cross. So h cross gets cancelled out. So the value will be ml divided by L into L plus 1 root over. So this is the value of cos theta. And if you calculate, theta will be cos inverse ml divided by L into L plus 1 root over. So is this clear to everyone? So this will be the correct option, option C. So is this clear to everyone?
Sure.
Hello?
Yes,
Okay,
sir.
so is
It's
that
clear.
so basically the question was if an electron is moving around the nucleus and it is placed in an external magnetic field. So when the electron or atom is placed in an external magnetic field, and we know that due to the electron motion there is a magnetic dipole and it has magnetic dipole moment or magnetic moment. So this magnetic moment will interact with the magnetic field, and due to this interaction there will be a torque experienced by the magnetic dipole, that is the electron, and the orbit of the electron will be revolving around the magnetic field by forming a cone which is called as Larmor cone, or the motion is called as Larmor precision, and the angle theta will remain fixed. And if you see the expression for Larmor frequency, which is EB by 4 pi m, it it is independent of theta, so what theta will remain constant throughout the motion, and the frequency of precision is EB by 4 pi m. So from quantization we know the magnitude of orbital angular momentum is L into L plus 1 into h cross, where this small l is the orbital quantum number, because L is the orbital angular momentum vector and L is the orbital quantum number and ml is the magnetic quantum number. The component of the orbital angular momentum along the magnetic field Lz is given as ml h cross. So if you put these two values, we found the angle between the two vectors, that is B vector and L vector, that is Lz vector and L vector, is cos theta will be Lz divided by L. So putting these values, we got theta is cos inverse ml divided by L into L plus 1 root over. I hope this is clear to everyone. Then let's consider the second question. Now, in the previous question, if L is 3, then how many possible values of theta are there? So can anyone tell me, if the value of L in previous case is 3, then how many possible values of theta will be there in the previous case? Yes, anyone? Yes, can anyone tell me if L is 3 in previous case, then how many possible values of theta will be there? So we know if the value is L, so we know if L vector, the value is L into L plus 1 root over H plus, and corresponding to each L, there are 2L plus 1 values of ml, that is the magnetic component. So if L is 3 here, so the number of components or the number of values of ml will be how much? Ml will be 2 into L plus 1, which is 2 into 3 plus 1, that is 7. So ml has 7 values. And what are those values? So the values of ml is plus minus 3, plus minus 2, plus minus 1, and 0. That is 3, 2, 1, 0, minus 3, minus 2, minus 1. So these are 7 values of ml. And since in the previous case we know cos theta is ml divided by L into L plus 1 root over. So basically this theta is gives the angle between L vector and Lz vector. Since it has 7 values, so cos theta will also be having 7 values. Is this clear to everyone? Yes. Is this clear to everyone or not?
Yes, sir. Yes, sir.
Okay, so uh, I think it's pretty simpler to the previous question, but I want to discuss a few things. So in last class, we talked about mu, which was mu L is E by 2m into L vector magnitude. And we know the, can anyone tell me what is this is magnetic dipole moment, magnetic dipole moment, and this L is orbital angular momentum. So if you um, take L vector to the left hand side, then mu L by L will be E by 2m. So basically this is a ratio of orbital magnetic moment to orbital angular momentum. And this quantity is called as, can anyone tell me what is this quantity called? Yes, anyone? Can anyone tell me what will be the quantity, what is the ratio of magnetic dipole moment to angular momentum is called as what?
Gyromagnetic ratio, sir.
Exactly. So this is called as gyromagnetic ratio. So can anyone tell me what is the significance of gyromagnetic ratio? So basically it is shows that how much magnetic dipole moment a dipole will produce due to its motion. If the magnetic dipole is orbital magnetic dipole moment, then from the orbital angular momentum or the orbital motion, that dipole moment is being produced. So this quantity signifies how much orbital or magnetic dipole moment will be produced due to a particular type of motion or angular momentum, angular momentum or angular motion. So if you see, this is mass of electron. This is mass of electron. Now similarly, if you consider proton, suppose proton, then mu L by L for proton will be E by 2mp. So now, if you see, the mass of proton is very, very larger than the mass of electron. So the ratio for proton will be very, very smaller in comparison to the ratio of electron, is not it? So what we got from this discussion, so the due to the motion of electron, it will produce larger magnetic moment in comparison to the motion of proton. Also, if you see this E by 2m, now in case of magnetic dipole moment or magnetic angular magnetic dipole moment or orbital magnetic dipole moment, we the unit, basically the general unit of mu L, general unit of magnetic dipole moment is ampere into meter square, because it is nothing but I into a, this this one I into a, so it is nothing but ampere into meter square, but this can again be written as in terms of joule per Tesla. And there is a unit of orbital magnetic moment. Sorry, there is a unit of orbital dipole moment, which is Bohr magneton. Which is called as mu B. We will discuss about it in more details in upcoming questions. So let's discuss the third question. The question says, the existence of spin angular momentum was established by Frank-Hertz experiment, Stern-Gerlach experiment, Thomson's experiment, and Raman's experiment. So yes, can anyone tell me the spin of electron or the spin angular momentum of the electron are established by which experiment?
It's Stern-Gerlach experiment.
Yes. So there are four options. Frank-Hertz experiment. So the second option is Stern-Gerlach experiment, the Thomson's experiment, and option 4 is Raman's experiment. So can anyone tell me uh, uh, which concept was explained by Frank-Hertz experiment? Yes, anyone? Yes. So Frank-Hertz experiment was basically uh, Frank-Hertz experiment basically explained the existence of excited levels in a atom. So like if the in the experiment there is electron collision, then some specific amount of energy will be supplied to the atom. So there are some certain amount of energy, or just otherwise we can or in other way we can say that there is some particular energy levels in which the electron can revolve. There is no energy level in between. So if the electron is giving some amount of energy, that particular energy will depend upon the energy difference between the two levels where the transition is occurring. Then option B, Stern-Galat experiment. Now Stern-Galat experiment explains the existence of spin angular momentum, and Thomson's experiment. Uh, I think Thomson's experiment. Let me. So Thomson's experiment was Thomson's cathode ray tube experiment. Then from Ramon's experiment, we obtained the Ramon's fact, that is there is a transfer of energy between the um, molecule and the electromagnetic radiation or photon. So these are the four experiments. Now let's discuss more about Stern-Galat experiment, how the experiments were performed and how it gave the idea about the existence of spin angular momentum. So the correct option will be option B, Stern-Galat experiment. And here the correct option will be option 7. Option D, answer is 7. So in Stern-Galat experiment, what they did, they took an oven. Suppose this is oven. They took an oven. Then they heated a silver atom. This is neutral silver atom. Neutral silver atom. Then these atoms are passed to different slits for their focusing. Then it was passed through magnetic field. So this is the magnetic field. 1 minute, let me. So it was passed through a particular type of magnetic field, which was non-uniform nature. If you see, this is north, this is south. Since this is some sharp edge here, so the lines of force will be like this. So here if you see, suppose this is Z direction and this is X direction. So the magnetic field is increasing along the Z direction. Now these silver atoms were passed to this non-homogeneous magnetic field, non-homogeneous magnetic field, and then they were collected in a slit or in a screen. So in a screen, we found that there are two distinct spots in a screen, like here one spot, here one spot. If you see horizontally, then the spot was something like this. So there are two particular spots. So why this happened? Because if you see here, there are two important factors. The one is the neutral silver atom. Why neutral? So they used Ag atom which are neutral. So why Ag atom? So if you see, can anyone tell me what is the atomic number for silver? It is 47. The atomic number for silver is 47. So if you arrange the atomic number of, if you arrange these 47 electrons, the last electron will be in 2s half orbit. 2s half orbit. So for 2s half, we know for s, L is 0. And since this is half, this is j, and this is 2s plus 1. So this spectroscopic notation is 2s plus 1 L j. So L is 0, S is half because 2s plus 1 is 2, 2s plus 1 is 2, which gives S is equal to half, and j is equal to L plus S, which is 0 plus half, which is again half. So here L is equal to 0, S is equal to half. Now we are taking S is equal to half because we know electron has spin, but how they determine there is some spinning motion of electron, because if you see in case of 2s half, there is no or L is zero, and we know the magnetic moment L vector is L into L plus 1 root over h cross. So mu L will be again zero, because the value of L will be zero. So there will be no interaction between the magnetic field and the, like in previous case we found there is a interaction between the magnetic field and the magnetic dipole moment, due to which there is some precision of orbit around the magnetic field. But here, since the last electron is present in the s orbit, and for s L is zero, so there will be no value of mu L, and it will not interact with the magnetic field. But since there are two different spots we are seeing here, it is interacting with magnetic field. Now, why there is non-homogeneous magnetic field? Because if the magnetic field is homogeneous, then there will be only torque, like it will rotate, but it will not experience some deflecting force, because here if you see, if it was not deflected, it will be coming like this. But in spite of the, but in place of that, it is coming to this point and this point, because it is experiencing some bending force. So this bending force will be given by Fz will be del B by del Z into mu Jz. So mu J is due to the total orbital quantum number, that is J, which is L plus S. Since L is zero for the 2s half, then there must be some other motion due to which they are being affected by this magnetic field, and then they are being deflected in two directions. So this Stern-Gallath experiment explained the effect of, or the presence of, the existence of spin angular momentum, because the due to the spin motion in a non-homogeneous magnetic field, they are experiencing some bending force, and due to this bending force or deflecting force, they are being directed in two opposite, or in two different points. So from this, we again found, like here, if you see in the previous case, we were saying if it is L, then there are 2L plus 1 values. So here there will be similar 2s plus 1 value. So this 2s plus 1 value is 2, because there are two spots. So this 2s plus 1 is equal to 2. So if you get, then from this we get s is equal to half. So the value of spin of electron is half. So the electron has spin quantum number s with value is half, and due to this half value, the electron has two different orientations in a magnetic field. So due to these two different orientations, there are two different type of force, because force depends upon the magnetic dipole moment. So since the value of s is different for both values, like plus half and minus half, so the force is different in different direction. So there are two different spots, and the electron are being incident on these slits. So everybody understood how the experiment was able to explain the presence of electron spin, or the existence of the concept of electron spin. Okay, so question, then next question, question 4. This question says, when an electron in hydrogen atom is in its fast Bohr orbit, when an electron in a hydrogen atom is in its fast Bohr orbit, then its magnetic moment is 9.28 in 10 to the power minus 24 ampere into meter square. Option B is 2.25 in 10 to the power minus 25 ampere into meter square. 1.70 into 10 to the power minus 28 ampere meter square. Or option D, 3.34 into 10 to the power minus 24 ampere into meter square. Yes, can anyone tell me what will be the value of magnetic moment if the electron is in fast Bohr orbit? Yes, can anyone tell me what will be the magnetic moment if the electron is in its fast core orbit? Yes, similar type of question we had discussed in the last class. So if you see, today we again discussed that there is a, so this is mu L divided by L is E by 2m. And if you see, suppose now Bohr orbit, for Bohr orbit, we know for fast Bohr orbit, for fast Bohr orbit, what will the value of n? N will be 1. Now, according to the Bohr's theory for hydrogen atom, we know the angular momentum L is equal to mvr is equals to nh by 2 pi. So, mvr will be h by 2 pi. If you, so this is the value of L. So when you put this, mu L will be E by 2m into L. It will be E by 2m into H by 2 pi, which is E H by 4 pi m. So this will be the value of the magnetic moment when the electron in hydrogen atom is in its fast Bohr orbit. So if you put all the values, so can anyone tell me what are the values of those constants? What are the value of E? Yes,
1.602 into
1.6
10 power
yes,
minus 19.
19 coulomb. Then what is the value of H?
6.625 into 10 power minus 34 joule second.
10 to the power minus
34
34 joule
joule
into
second.
second. Then we know the mass of electron is 9.1 into
9.1
10 to the power minus
10 power
31
minus
kg,
31 kg.
pi is 3.142. So put all these values and tell me what is the value of mu L. I request everyone to mute themselves.
Here it's 9.274 into 10 power minus 24.
Yes, so
9.274 into 10 power minus
yes,
24.
yes, so this is the correct answer. So this value has another name. Can anyone tell me what is it called?
Oh,
This is
9.2.
how much we get? The value is how much? 9.28
4
into 10 to the power minus 24. Yes?
magneton, sir.
Yes, this is Bohr magneton. Bohr magneton. So all the atomic magnetic dipole moments, whether it be orbital or spin dipole moment, all are expressed in terms of Bohr magneton only. And the value of Bohr magneton is 9.28 in 10 to the power minus 24. So this Bohr magnet nothing but E h cross by 2m, because if you see, we knew this is mu L vector by L vector is E by 2m. Then how this value came into picture? Now we can also write mu L vector is equals to GL into E by 2m into L vector, where G is orbital G factor, orbital G factor, and GL is 1. Similarly, if you talk about S or spin moment, then spin will be, mu S will be GS into E by 2m into S vector. So if you see here, in case of this, GS is 2, which is spin G factor. Why this is 2? Because for S is equals to half, there are two values. So the factor is 2 here. So mu S will be GS E by 2m into S vector. We know. So if the uh, electron is present in the first Bohr orbit, then n is equal to 1. So from this formula, we get h by 2 pi or h cross. So MBR is h cross. Then if you put this in this formula, it is E h cross by 4 pi m. This E h cross by 4 pi m is known as Bohr magneton. Then the representation of orbital magnetic moment and orbital angular momentum is mu L is equals to GL into E by 2m into L vector. This is for orbital motion and this is for spin motion. So these are the two expressions for calculating orbital and spin magnetic moments. Then the fifth question, the question says, for the 3p spectroscopic term with spin orbit interaction, the possible values of J are, the option A is 0, 1, 2, option B is 1, 2, 3, option C is 0, 2, 3, and option D is -1, 0, and 1. Yes, anyone? Can anyone tell me? Yes, can anyone tell me what will be the possible values of J? Yes, anyone? So we know when there is an external magnetic field, in previously we knew the L vector is preceding around the magnetic field. But now we found that L is orbital angular momentum. And in addition to that, there is another spin motion which is spin angular momentum. Now, due to these two, now corresponding to this orbital angular momentum, there is magnetic moment, which is orbital magnetic moment mu L, and there is spin magnetic moment mu S. So, these two magnetic moment interact with each other. When the magnetic field is weak, then these two magnetic moments interact with each other, and as a result, there is a total angular momentum, which is J vector, which is the sum of L vector and S vector. So if this is B, then this is L vector, and this L and S, is, this is around the total angular momentum J vector, and this angular momentum J vector, it undergoes Ragnar friction around the magnetic field. So this is L vector, suppose this is L vector and this is S vector, then this L plus L will be J vector. This is J vector. Now this S precesses around J, this L also precesses around J, and this J precesses around the magnetic field B vector. So in this case, this is called as spin orbit interaction. Why it is called as spin orbit interaction? Because the spin orbit interaction is dominant over the magnetic field and the angular momentum interactions. So there is interaction between L vector and S vector. As a result, there is J vector. So the magnetic field affects only the J vector, and L S vector as a sum give total orbital angular momentum J vector, and this J precesses around the magnetic field vector. Now if you see, we know J is L vector plus S vector, they are added vectorially. So if L vector has value L and S has value S, then the value of J is L plus S to L minus S with one increment. That is, if L is equals to 0 and S is equal to 1, then J will be 1 plus 0 to 1 minus 0, which is 1 only. But if L is equals to 1 and S is equals to 1, then L plus S is equals to 1 plus 1, 2, L minus S is equals to 1 minus 1, 0. So the value of J will be 0, 1 and 2. That is L plus S, which is 2, L minus S is 0 with 1 increment. That is 0, 1, 2. So this will be 3 values. So in question, it is given for 3P spectroscopic term. So here you can clearly see 3P means what? We know this 3 is 2S plus 1. So this 2S plus 1 is 3. So it gives S is equals to 3 minus 1 by 2, which is 2 by 2. That is 1. So S is 1. And for P, L is 1. So L is 1 and S is 1. So the possible values of J is L is 1, S is 1. So possible values of J is J 0, 1, and 2. So the correct option will be option A. The possible values of J are 0, 1, and 2. Is this clear to all of you? Yes? Is
Yes,
this
sir.
clear to
Yes.
all of you? Okay. So this is nothing but the vector model of atom, that is all the quantities are represented as vectors. Due to orbital motion of electron, there is orbital angular momentum, and due to this orbital angular momentum, there is orbital magnetic dipole moment, which is mu L. Similarly, due to spin motion, there is spin orbital angular momentum, there is spin angular momentum, and then there is spin magnetic dipole moment. So when these two interact with each other and the magnetic field is weak, then they don't interact individually with the magnetic field. In this place, they interact with each other, and as a result, there is a third angular momentum, which is called a total angular momentum. The value is J vector is equal to L vector plus S vector. Like these expressions mu L and mu J, there is mu L and mu A, there is mu J also, which is Gj into E by 2m into J vector, where Gj is called as Landé G factor, and the value of Gj depends upon the value of the labels. So the correct option here will be option 0, 1, 2, because L is 1 here, 3p means L is 1, because the spectroscopy notations are 2s plus 1 L J. So 2s is 3, which gives s is equal to 1, and p for p L is equal to 1. So s is equals to 1, L is equals to 1. This gives j is equals to 1 plus 1 to 1 minus 1. So 1 plus 1 is 2, 1 minus 1 is 0, and with 1 increment, values are 2, 1, and 0. Then question number 6, an atom with one outer electron having orbital angular momentum 2 is placed in weak magnetic field. The number of energy levels into which the higher total angular momentum state splits is what? The option A is 1, option B is 3, option C is 5, and option D is 0. So can anyone tell me if an atom is in so an atom with outer electron having orbital angular momentum 2 is placed in a weak magnetic field. So the number of energy levels into which the total angular momentum state will split. Yes, can anyone tell me the number of levels into which the higher total angular momentum state is split into? So as we know, if the value is L, then the number of labels splitted is 2L plus 1. So here the value is 2. Then the number of labels it will be splitted is 2 into 2 plus 1, which is 5. So the correct option will be option C, which is 5. Then question 7. The last two terms of the electronic configuration of Mn atom is 3d54s2. The term factor for Mn4 plus ion is what? Yes, the options are option A 4d half, option B 3d 7 by 2, option C 3f 9 by 2, option D 4f 3 by 2. Yes, can anyone tell me what will be the last, what will be the term factor of Mn4 plus ion? So if you see here, the electronic configuration of Mn is 3d5 4s2. So Mn4 plus. So since this is filled, so the 4 plus means it has 4 lesser electrons. So the electrons will be coming out from these levels. So here there will be 3d1 4s2. So if you see here, the last electron is in 3d1. So for this 3d1, d means L equals to 2, and for one electron, S is half. So J is L plus S to L minus S. So 2 plus half and 2 minus half. So J will be 2 plus half equal to 5 by 2, and 2 minus half equals to 3 by 2. So there are two values of J. So here you see in the options 5 by 2, 3 by 2 is available only in the option D. which is 4F 3 by 2. So the correct option here will be 4F 3 by 2. So if you see here it is 3 by 2, then J will be 3 by 2, 2 into 3 by 2 plus 1, which is 3 plus 1, 4. So here it is 4F 3 by 2. Here it is term factor. So 2S plus 1 LJ is not valid here. So it is 2J plus 1 LJ. So 2J plus 1 LJ, which is 4. L is 2. So it is, so L is, so this 3 by 2 is the only available option. So it is 4F 3 by 2. 4F 3 by 2. So this is the correct option, option D. Then question 8. In how many lines the D1 line of sodium, which corresponds to the transition 3p half to 3s half, will split in presence of weak magnetic field? So options are option A 1, option B 2, option C 3, and option D 4. Yes. So can anyone tell me in how many lines the D1 of sodium, that is 3p half to 3 2p half 3 2s half, will split in presence of weak magnetic field? Yes, anyone? So yes, can anyone tell me in how many lines the D1 line and the D1 line, which correspond to transition between 2p half and 3s half, will split in presence of weak magnetic field? Yes, anyone? So if you see, I just discussed, in case of weak magnetic field, what happens? Now if you see here in 3p half, sorry, so here 3 is nothing. Here 3 is n. So here this 3 is n. So here the actual terms are 2p half and 2s half. So this 2 means 2s plus 1, which is 2. S is equals to half. And here p. P means L equals to 1. So the value of the total angular momentum J is L plus S and L minus S. So J will be for P half. To P half, J will be 1 minus half and 1 plus half. So half and 3 by 2. So this will be the values of J for 2P half. Similarly, for 2S half, we have S equals to half and L equals to 0. So J will be how much? J will be half. There will be only half. So here you see there are two levels. In case of P, if you see 3P, there is one 3P half and 2P 3 by 2. So here in question it is given 2P half to 3S half. So here you see when there is a weak magnetic field, then there will be only the interaction between L vector and S vector. So only the number of energy levels it will split will depend upon the value of the angular momentum, total angular momentum J. So here for 2P half, so it is not needed here because only the transition is given from 2P half to 2S half. This is D1. Similarly, D2 line corresponds to 2P 3 by 2 to 2S half. So there are two lines, but here we will consider only one line, and in presence of weak magnetic field, in how many lines it will be splitting. Basically, this effect is nothing but the G-man effect. There are two types of G-man effects. One is normal G-man effect, and another is anomalous G-man effect. In case of normal G-man effect, there is spin is 0, but here if you see the spin is not 0. So this is anomalous G-man effect. So now you see here, since the magnetic field is weak, the interaction between L vector and S vector will be there. So the total angular momentum J vector will play the dominant role here. So since P is here, J is half, the label it will split into 2J plus 1. That is 2 into 1 by 2 plus 1, which is 1 plus 1 is 2. So similarly for 2S half, it will again split into two labels because 2J plus 1 is 2. So now this is 2P half. This is J equals to half, J equals to minus half. 2S half, J equals to half, J equals to minus half. Now the transition rule is delta J is equals to 0 plus minus 1, where 0 to 0 is not allowed. So here if you see, there will be how many transitions? In J, from J equal to half, there will be J equal to half, because half minus half 0 is allowed. Then again from J equal to half to J equal to minus half, because half minus of minus half is plus 1, so it is allowed. So from J equal to half, there will be two transitions. Similarly, for J equal to minus half, one transition will be from J equal to minus half, because minus half plus half will be 0, it is again allowed. And the fourth transition will be J equals to half to, sorry, there will be not, this is not the transition. The actual transition will be from here to here. Half minus of half is equal to 0, it is again allowed. So there are four transitions, and due to these four transitions, there are four lines. So the number of lines, the D1 line of sodium will split in presence of weak magnetic field is 4. Similarly, if you see in case of D2 line, can anyone tell me if this is the transition correspond to D2 line, then how many number of lines the D2 line will be splitted in case of weak magnetic field? Yes. Can anyone tell me? So in case of, since it is 3 by 2, there will be 3 by 2 into 2 plus 1. That is 4 levels. So here the upper one is splitting into 2 levels, but there the upper one will be splitting into 4 levels. So there will be 6 allowed transitions. So the D1 line splits into 4 lines in terms of weak magnetic field, but the D2 lines split into 6 lines in case of weak magnetic field. Is this clear to everyone? Yes.
Yes.
Okay, so question 9, it says a beam of electron enters a uniform magnetic field of B Tesla. Calculate the energy difference between the electrons whose spins are parallel and anti-parallel to the field. Where E is the charge of electron, M is the mass of electron, and H is Planck's constant. So this is a very good question. Here, if you see, since the electron has some spin, it will be having some spin magnetic dipole moment, and when the spin dipole is placed in a magnetic field, then there will be interaction between them, and due to interaction there will be some energy. Here the question says calculate the energy difference between the electron whose spins are parallel and anti-parallel to the field. So since it is a cross product, that is, we know the value of energy or the interaction energy between a magnetic dipole and a magnetic field is given by how much? N by E is equals to minus mu s dot B vector. So since there is a dot product and it depends upon the angle between these two vectors. So when the motions are parallel and the motions are anti-parallel, there will be two different energies. And here we need to find out the difference of the energy between these two types of electrons. That is one group which are being moved parallelly and another which are moving anti-parallel to the field. So the options are EHB by M, EHB by 2 pi M, EB by 2 pi HM, then MB by 2EH. So these are the 4 options. So I will give a few minutes to try this, then we will discuss. Yes. So can anyone tell me what will be the difference in energy? Hello, am I audible to all of you?
Sir, yes, sir.
Okay, so here you see, we know mu s vector is equals to minus E by 2m s vector. Here there is another factor gs, which is spin g factor, and we know gs is equals to 2. So if you see, the mu s vector mod will be how much? The mu l vector mod will be E by 2m, 2e by 2m into s vector mod. It will be E by m s vector mod. Now the magnetic field is along suppose the magnetic field is along z direction. Then what will be the value of mu s z? Mu s z will be E by m into sz, and we know sz is nothing but ms h cross. So the value of ms is plus minus half. So one is plus half, another is minus half. Plus half is along the direction of magnetic field, minus half is antiparallel to magnetic field. So we need to find out these two values. So for one, it is plus half, and for another, it is minus half. So when s is equals to half, then what we get? Mu s z is E by m into half into h cross, or eh cross by 2m. This is mu s z. Then s is equal to minus half, then mu s z will be minus eh cross by 2m, because here only minus one factor will be coming. So now the question says, calculate the energy difference. Now the potential energy in a magnetic field is given by E is equals to minus mu L into B vector will be minus mu S Z B, because here cos theta, here the component along B vector is mu S Z. So now there are two values of U S Z. So one value, so delta E will be, so delta will be U1 minus E2. So U1 is how much? U1 will be, so these are two values, which is EH by 4 pi m. This is nothing but EH cross by 2m is nothing but EH by 4 pi m. So one value will be EH B by 4 pi m, minus another will be minus EH B by 4 pi m. Because here if you multiply, when the value is, it is moving along the magnetic field, then the value of mu is a plus half. So if you put here plus half, then it will be minus. Then it is antiparallel to magnetic field. Then you put it minus half, then it will be plus. So one value will be EHB by 4 pi m, another value will be minus EHB by 4 pi m. So if you add both these, it will be EHB by 2 pi m, because so this is the difference in energy when the electron are, so one electron is moving in parallel, another electron is moving anti-parallel. So the spins are parallel to the magnetic field and anti-parallel to magnetic field. So the options are EHB by 2 pi m. EHB by 2 pi m. So the correct option is option B. Is this clear to everyone? Yes. Here you see,
Yes.
since there are different motions of electron, the value of mu h z is different. So one motion is along the magnetic field, another is in opposite direction to magnetic field. So due to this, there are two different energies, and the difference in energy is EHB by 4 pi m minus of minus EHB by 4 pi m. So the total energy difference is EHB by 2 pi m. Now, question 10. Find the two possible values of states for a d electron in one atomic electron system. Option A is 2d half, 2d 3 by 2. Option B is 2d 3 by 2, 2d 5 by 2. Option C is 2d half, 2d 5 by 2. And option D is 2d 5 by 2, 2d 7. So can anyone tell me what will be the two possible values or two possible states when a single electron is present in d level or d cell?
Sir, question paper is not visible, sir.
Sorry, it is not visible.
Yes, sir. Now it is visible. Previously, the last screen only we have seen.
Yes. So is it now visible?
Yes, sir. Is it clear?
So the question says find the two possible states for a d electron in one atomic electron system. So there is a single electron, there is one electron, and that electron is present in d cell. So what will be the two possible states? The options are 2d half, 2d 3 by 2, 2d 3 by 2, 2d 5 by 2, 2d half, 2d 5 by 2, 2d 5 by 2, 2d 7 by 2. So these are the two options. These are the four options. So can anyone tell me what will be the possible values of states?
Option B, sir. D3 by 2 D.
Once again,
B, sir. Option B.
yes. Option B is correct. So how we can calculate? So here the question says it is a one electron, one atomic electron system. So for one electron, we know, can anyone tell me what is the value of S for one electron?
Up.
It is half. Then since it is D, then what is the value of L?
2, sir.
2. So we know if S is equal to half and L equals to 2, then J value is L plus S mod to L minus S mod with the difference of 1. So L plus S is how much? L plus S is 2 plus half, which is 5 by 2, and L minus S is 2 minus half, which is 3 by 2. Is not it? So there are two values of J. So J will be 3 by 2 and 5 by 2. For both these values, for these values, L is 2 and S is equals to half. Now, according to spectroscopy notation, it is 2S plus 1 Lj. So 2S plus 1 will be how much? 2 into half, because S is equals to half here. S is equal to half, only a single electron, one atomic electron system. So it will be 1 plus 1, which will be 2. Then we know J is 3 by 2 and 5 by 2, and L is 2, so it will be D. So the two states are 2D 3 by 2 and 2D 5 by 2. So this is the correct answer. So the question was find the two possible values of states for a d electron. So when the electron is present in a d cell, the value of L is 2, and when there is a single electron, the S is half. So according to vector atom model, the value of J will be L plus S to L minus S. So 2 plus half and 2 minus half. So there is only increment means there is only one increment. So it will be 3 by 2 and 5 by 2. So for J is equal to 3 by 2 and 5 by 2, and L equals to 2 with S equals to half. The two labels are 2D 3 by 2 and 2D 5 by 2. So can anyone tell me whether 2D 7 by 2 is possible or not? This energy level is possible or not? Yes, is it valid expression or not? So if you see, if you are writing 2D 7 by 2, then J is 7 by 2. J is L plus S. Here we found the two available values of J is 2 by 3 by 2 and 5 by 2. So it is not possible. Also, D half is not possible. Is this clear to everyone? So here,
Yes, sir.
this is not a valid expression or this is not a valid expression. And we also know that the increment is always 1. So this, since here is also half is present, so it is not a valid expression or valid spectroscopic term. So the correct option is option B, which is 2D 3 by 2. Then last question of today's session, calculate two possible orientations in degrees of spin vector S with respect to magnetic field direction. The options are 54.735 degree, 125.264 degree, 72.25 degree, 105.84, 28.275, 98.75, 14.15, and 175.245. So these are the four options. So can anyone tell me what will be the two possible orientations of spin vector with respect to the magnetic field direction? So this is nothing but the space quantization. That is, since we also know that there is some the values of spin is also quantized because it is uh, half or minus half. So the orientations is also quantized. Orientations can't be in all available directions. It is the orientation can only be possible in some particular direction. So that particular direction is represented as magnetic quantum numbers, which is spin magnetic quantum number or orbital magnetic quantum number, which are ms or ml. So since the electron has spin s is half, so what will be the value of ms? Plus half and minus half. These are there are two ms values. So there will be two angles between the spin vector and the magnetic field. Because we know if this is the magnetic field, then this is Sz and Sz is ms h cross. So there are two Sz values and S is S into S plus 1 root over into h cross. So there will be angle theta cos theta is ms h cross divided by S into S plus 1 root h cross. It will be ms divided by S into S plus 1 root over. So can anyone tell me what are those two values? Yes, anyone? Can anyone tell me what will be the two possible values? So you know cos theta equals to ms divided by S into S plus 1 root over. ms is half and minus half. S is half. So theta 1 will be cos inverse half divided by half into half plus 1 root over. It will be cos inverse 1 by 2 divided by 1 by 2 into 3 by 2 root over. It will be cos inverse 1 by root 3. Theta 2 will be cos inverse minus 1 by root 3. Because here only minus half will be there. Minus half divided by s into s plus 1 root over. So it will be only minus. So cos theta 2 will be minus half into 2 by root 3. 2 gets cancelled out. It will be minus 1 by root 3. So can anyone tell me what will be the two theta values? Yes, anyone? Yes. Can anyone tell me? So one value will be 54.735. 54.735 degrees. Another value will be 180 minus 54.735. It will be 125.265. So these are the two values. And from option, this is the correct option, option A. So if this is the, so there are two different values. One is in like this. So this is 54.735 and this is 125.264. So these are the two values. Is this clear to everyone?
Yes, sir. Yes, sir.
Okay, so is there any doubt in any problem we discussed today, or any other doubts related to the class contents?
No, sir.
Okay, so I thank you all again for joining in today's session. So in the next session, we will discuss some more problems related to the fine structure of hydrogen atom and quantum mechanical treatment of hydrogen atomic model. So how due to the introduction of quantum mechanics, how the changes are appearing in the Bohr's atomic model that was given by Bohr, and there is some energy corrections. So with all these we will be discussing in the next introduction session. I again thank you all. Have a great day.
Thank you, sir. Thank you.